Our first speaker is Professor R.P. Singh, and he is popularly known as RP, and even he has hidden that Singh part in the name on the slide also, it's RP. So he did his PhD from JNU, then he was subsequently in University of Hyderabad, and for many years he was associated with Physical Research Laboratory, where he did many interesting experiments involving nonlinear optics, quantum imaging, entanglement generation. And in the recent past, they did experiment on BBM, implementation of BBM protocol over free space. And he did other experiments on free space on quantum cryptography, and this tutorial will be focused on quantum cryptography. So over to Professor R.P. Singh, and as before, please keep your mobile phone in silent mode and ask questions whenever it comes in mind.
Thank you, Anirban, and thank you, Chandru, for inviting. Basically, I asked Chandru that I want to learn something theory. I have not been attending seriously conferences because being a senior faculty member, head of the division, you hardly find time. You are always going around reviewing the projects or taking interviews and all those things. So many file loads. So I was not getting time. I asked Chandru that I want to learn and I want to come to the conference. So Chandru said that you have to give talk, then tutorial. So that's how this tutorial has come, all this theory conference. So I am here basically to learn from you guys instead of giving you like what I am doing. So our title he gave State of Art in India. So there are many groups in India. I will refer, but I will not go into detail what they are doing, how they are doing. But I will certainly refer, maybe not in slides, but I will refer as we go along. But what I am going to discuss, what we do at PRL, okay, what we do, so that I can explain what we have done. But this is not the only work which is being done in India. That's why I've removed India. Okay, so there are many groups in India. They are doing experiments, not only theory. And this work also which I am presenting, there are so many guys involved. And if you work with experimentalists, you are guys interested in theory, if you work along with experimentalists, it really pays. Literally it pays. Because one of my students, our student Anil Banerjee, who is doing postdoc in NUS, he started working with us like modeling experiments, closely with experiments. Earlier he was doing Wigner distribution function, non-negativity and all those things he was doing. He had papers and all those things, purely theory. Then he started working on experiments with us. And then he went to NS and he started working with experimental group. And after, in third year, he was given independent charge of developing quantum memory and experiment as well as theoretical simulation. And he started working. Now he's being offered a job, $2,000 per annum and with other benefits. Okay, just young guy, $2,000 per annum and other benefits along with that. 2,000 come nahi hai. 200,000, sorry. I'm really sorry. 200,000, you're right. 200,000, because I can't imagine even that. 200,000 that fellow is getting, okay, per annum. So it really pays if you work along with experimentalists, theory guys, so it pays. So there are many guys, young faculties are also there, Sashi and Gautam, they are and they're engineers also. It's not just like physicists, they are engineers also involved in this group and they contribute to the. So everybody knows here what is quantum key distribution, why it is important. So basically I'm talking about experiments. So how you do, what are the things involved? So most of the prepare and measure protocols, prepare and measure quantum key distribution protocol, they don't use single photon source. They use weak coherent pulses. Okay, that's what they call weak coherent pulse. And you take a pulse laser and reduce the intensity in such a way that mean uh, mean photon number per pulse is less than one. So that's how you do. And but it's not a single photon source. One should understand it's approximation to a single photon source. However, you can make a single photon source, heralded single photon source, or even on-demand single photon source using SPDC or quantum dots. Okay. So SPDC gives you heralded single photon source, but instead of SPDC, you can use quantum dots, and you can have a deterministic single photon source. And people are working on that. And what you do here, as I told here, you can reduce the intensity, but laser is laser. It has certain photon number distribution. It follows Poissonian distribution. Even you have reduced intensity in such a way that mean photon number per pulse is less than 1. There will be pulses which will have more than 1 photon, and it may lead to serious attacks on the QKD. So these entangled photons and heralded single photons, you can use nonlinear crystal and laser, and you pump this nonlinear crystal with laser, and 1 photon of the laser gets converted into 2 photons. This is spontaneous parametric down conversion, so lower energy photons. And these 2 photons are produced simultaneously. So that's why they can use as a heralded single photon source, because they are coming together. Presence of one heralds the presence of other. Like detection of one heralds the presence of other. So that's what it is, heralded single photon source. And how you verify that it is single photon source? Okay. So if it is single photon source, what you do Hanbury-Brown twist, high intensity correlation experiment, and G2 0 should be almost 0. So that's what you do. In heralded single photon source, how you verify? Suppose you have just one single photon coming, you can put beam splitter, you can do 2 detectors and see the coincidence. If there is only 1 photon, if there is only 1 photon, this beam splitter is there. Okay, one will go there, one will go there. You have detectors, so there won't be any coincidence counts. Okay, because 1 photon it will go only this side or this side. So there won't be coincidence detection in this detector. Means at the same time both of them will not click. Okay, so that's how you verify there is only 1 photon. If it is single photon, but in heralding what you do, you have now this branch, you put detector here, this branch, you put beam splitter here, okay, and then one will go this way. You have 3 detectors now. So you have to do coincidence counting for these two, and all 3. So using this coincidence counting, you can find out whether you can calculate G20 for a single photon source, and you can verify that it's a single photon source, and it should be almost 0. As close 0, it's better single photon source. Like we obtain 0.02, 0.03, something like that when we do experiments. So that's how you do a single photon source. And entangled photon source, because they're coming together, in certain variables they are correlated. So most of the time we go for polarization entanglement, okay, because you can easily measure polarization, okay. So you see that in polarization they are correlated. So they are entangled in polarization. It doesn't mean like they are entangled, but they are correlated in all the variables. You can say entanglement polarization because you see the correlation in their polarization properties. So that is the thing. And transmission channel, it can be fiber or free space. This is photon. Using photons only you do. Quantum key distribution, they are flying qubit. They don't interact. So transmission channel or quantum channel, because it transmits the quantum states. So that's quantum channel. And free space as well as fiber can be taken as quantum channel. Detectors, you use single photon detectors because you are working with photons. So single photon detectors can be avalanche photodiode based as well as superconducting nanowire single photon detectors. Both you can use. They are much more sensitive. Quantum efficiency is very high. Dead time is less. Jitter is less. But they are very costly and bulky. They have like quantum efficiency good, but not so good compared to SNSPDs. But they are compact and they are a bit less expensive. Not too cheap, but less expensive. And then if you want to you do CVQKD, you have to use homodyne detectors instead of the single photon detectors, because we use continuous variable. We are measuring continuous variable. So when you do QKD, you can have prepare and measure as well as entangled photon-based quantum key distribution. I am showing you free space, but you can use fiber also. You can connect like 2 parties. Here 2 parties are satellite and ground station. You can have 2 parties at the ground if you are doing fiber, and you can connect through fiber. Of course, when you are doing with fiber, instead of polarization, phase is preferred variable. So you work with phase because relative phase remains fixed. And polarization, as polarized state, the polarized light goes through the fiber, it changes the polarization. But people use polarization also in fiber, but preferred variable is phase. So you do the distributed phase difference thing when you are using fibers instead of polarization. So you can have trusted node quantum key distribution as well as untrusted node quantum key distribution. When you are using prepare and measure, you do trusted node because nodes are having key information. Anybody can access that key from the node. So that's called trusted when you are doing prepare and measure. So that's what satellite is doing. You can do with fiber also, trusted node. Okay, when you are doing prepare and measure, you have to trust the node that nobody is taking have access to those keys which are being stored there. So this is satellite here. It's prepare and measure protocol. States are being prepared in the satellite and they are sent to the ground station. Ground station with measurement. What is ground station? Basically, it's a telescope along with detection. And if you are doing long distance, this free space thing, you have to have very good pointing, tracking, and acquisition system of the signal, which signal is coming from satellite. And it's not only satellite has to be like signal has to come from satellite. This is called downlink. You can have uplink also. Signal can go from the ground to the satellite. So accordingly, this experimental arrangement will change. There you have to put detectors and everything. The state has to be prepared here and transmit to satellite. So this is the prepare and measure protocol. Here, this state is being gone. So state is being prepared in the satellite. I don't know. Sometimes it comes very feeble. Yeah. So this satellite, so this they are having keys, and then goes to another station, and again you have keys. Two stations are now. Satellite is having key K and KB. Uh, Through two stations, then one can have jar operation. Rahul has explained, and then you do the another jar operation. You have same key at both the stations. So you have KB, you do the jar, you send the jar signal, okay, encrypted signal, do another jar operation. You have same key here. Now you can have secure communication. So this is trusted node because satellite is having key information one can extract. Yeah, it can. Yeah. So So you have to take, yeah, so you have to use very good spectral and time filtering. So you have to know exactly when you are sending and when you are receiving, if you can do. And if you have very nice filters, which will select only that wavelength, so you can improve that. And then you have to take care of the thing that background at that wavelength is less. So you have to select that background. Suppose you want to do in daylight. So in daylight, which wavelength will having less background, you have to select that. And you should have good detectors for that wavelength. So many considerations involved. So outside the visible spectrum, yeah. Yeah, infrared, yeah, near infrared. So that's why you have to select the filter. You have to take the filter, very narrow filter, which selects only the signal. Okay, cut out the background, and because background is less at that wavelength, you will have like more signal. Yeah. So there is a beacon laser they use. Okay, reference laser, beacon laser they call. Okay, I will show you some experimental for short distance. Same principle is used in long distance also. You have to use some reference laser, beacon laser to check the alignment. If that is coming, giving signal, then you send the signal, it will be received. Yeah, laser is you can send to moon and all. They are doing like lunar optical communication already. There will be deflection, divergence will be there will be beam wandering and all those things. Still, you get enough signal at the ground. That's why you use large aperture telescopes. There are so many things here. So very high. So you can do that. So this is trusted node. Then there is untrusted node. Here satellite is having entangled photon source, and these two photons, these entangled photons, they are being sent to the two stations, and these stations make measurement, and based on the measurement they develop the key. And now once they have the key, they can do the secure communication. Here this satellite is not having any information about the key; it's just having entangled photons. So it's untrusted node, so you call. So when you are doing entanglement photon based, even in like simple fiber thing, it's untrusted. You are not keeping keys there. Rather, I will tell you. Sometimes people ask, what is the key generation rate? How, like whether you are using KB or megabit per second. But what happens because of this? I am saying you are not storing the key. If you are generating large number of key, you have to delete rather. You have to have that much key which you are consuming. Okay. If you are not consuming or storing, then it is security hazard. So there are systems like in NUS. If you go, you might be knowing they are testing many systems. Toshiba, ID Quantic. There are other companies, Quantum Sense Lab, which have developed quantum key distribution system. So they are saying you have to discard the keys because they are generating so much and you are not using. So it's a security hazard. So and why? Because either you use the key length which is equal to the like your message which you want to encrypt, or because you can't generate such high like gigabit, suppose file is there, you have to encrypt, send that you are not able to generate using quantum key distribution. So they use AES. Using AES you have to just take 128 or 256 bit, and with that you can encrypt gigabits of file. Okay, so you're using hardly kilobits of keys per second to encrypt the files to send the message, secure message. Rest of the key they discard. So they are like of the opinion key entanglement based this quantum key distribution is good enough. You can generate that many keys which can be consumed on the go. You need not to store. So here you see that one can have quantum key distribution using discrete variable as well as continuous variable, and both are having prepare and measure based and entanglement based protocol. Okay, here you are measuring like photons. Okay, photon detection. Here you are measuring field. You can say what is the quantization. So each photon will have associated field. So you're measuring that field associated photon. It's not like electromagnetic field. It's field associated photon. That's what you are measuring, trying to measure. And because you are measuring field, you use photo detectors instead of single photon detectors, and they have entanglement base, so there they use squeeze light. Otherwise, prepare and measure, like here, prepare and measure use weak coherent pulses. They use weak coherent states, and then Gaussian modulation based protocols are there. How you are modulating your signal, and discrete modulation. So you are having discrete modulation. So quadrature phase is quarter phase shift keying, quantum, this quadrature amplitude modulation, and this is like G.G. Grossan and Granier, I think. So they developed this. Here you modulate phase as well as amplitude. Here basically you modulate either phase or amplitude in discrete modulation. So at PRL we are working on both like discrete variable as well as continuous variable quantum key distribution. So some of the results which we have done already published, like rigorous characterization of mean photon number purpose. This is very important because all weak coherent pulse protocol start with that. What is your mean photon number purpose? Everything is based on that. So you have to do the rigorous characterization of that. We have done that, and then side channel information, side channel leakage. You have to calculate properly source side as well as detection side. Both sides we have done this side channel leakage calculation, and you have to take into account for your system when you go for privacy amplification. So experimentally you can verify what is the side channel leakage. Then we have developed one new quantum key distribution protocol that's called coincidence detection protocol, and along with that we have developed entrapped pulse coincidence detection protocol, and then we have used entangled photons. We have developed very good entangled photon source, very stable, very compact, and we have used it for entanglement based quantum key distribution. We have studied the effect of atmosphere on the quantum key distribution free space. Then we have done the integration of fiber-based QKD with free space QKD. We are working on device-independent quantum key distribution protocol, and working on entanglement swapping in free space. Let's see how much time it takes. Um, then uh, working on CVQKD, we have some of the results here. I will not go into detail. I don't have much time. I think 1 hour, or I would like to finish before 1 hour so that we can have discussion. So, so this is the general like schematic when you are going from prepare and measure based quantum key distribution protocol. Anyway, it has been shown already. I think um, Professor Singh has, Pranav has shown that. So I will not go into detail. This classical and quantum both are important. This communication for quantum key distribution, just for quantum state, will not have communication, a quantum key distribution. You have to share the time stamps and basis reconciliation using classical channel. So most of the time, till now, we are using for authentication and our classical channel as internet protocol, this internet thing. But so this is the general schematic for BB84 protocol. Since you are like mainly theory, I will go much more detail here. So these are the four laser diodes. You can have 8 for decay state, or same four lasers you can in time you can use for decay state. Okay. So if you are being economical, same four lasers can be distributed for decay thing. So here this is the electronics FPGA field from gated array device. So it randomly switches these lasers. Okay, random switching is done, and these random numbers are generated here. And this is a wave plate, half wave plate. This is half wave plate. This is polarizing beam splitter, and this is again half wave plate. This is beam splitter. So what is the difference between beam splitter and polarizing beam splitter? Beam splitter combines the signal or split the signal. Both it does. Okay, it combines also. Two signals get combined. They are being one is transmitted, one is reflected. So they are get combining, and it splits also. So both it can be used for both. So here four signals like and the four polation states are being combined and being launched. So half wave plate, what it does, suppose you rotate, there is fast axis, okay, of the half wave plate. This is polation optics. If you rotate it by 22.5 degree, this linearly polarized light will be rotated by 45 degree. So you can create, and this half wave plate and polarizing splitter combination can be used for reducing the intensity also. Okay. So this can be used for reducing the intensity because PBS passes only horizontally polarized light, and with half a plate you are rotating the polarization. So you can reduce the intensity as well as you can prepare a particular polarization state. So that's what it is being used. So you reduce the intensity, and this where this second half a plate is being used here. Here you are preparing a diagonal and diagonal and anti-diagonal polarization state. Okay, we call diagonal basis. And here, just reducing the intensity, this PBS half a plate. So here you are preparing horizontal and vertical, we call rectilinear basis. So these two four states being randomly generated, and they are being launched. So this is optics now. This is the laser basically, what I was talking. This is the reference laser, a Bacon laser. This is for 200 meter quantum key distribution, 300 meter, both we have done. And then this you send this beacon laser, reference laser, to check the alignment that you are getting the signals here. Once you verify with this beacon laser, reference laser, then you send the real quantum signal and you measure the signal. That's what you do. So this is the collection optics. And then you have to have time stamps. That's very important for both, like when it was generated, when it was received. And here if you notice that, here this is beam splitter at detector side. This is not very good, I don't know. At detector side, you see here, this is beam splitter. So it does the like passive randomization. So passively it will pass, sometimes it will go here. We are talking of single photon, weak current pulse, but approximate to single photon. Sometimes it will go here, sometimes it will go there. So it's a random thing it's doing, randomization. And then here half wave plate and PBS. So it will like diagonal and anti-diagonal basis. So one will like, where this diagonal polarization will go, where anti-diagonal will go. Same way here, this is PBS, so horizontal will pass, vertical will get reflected. I think this is wrong. It should be like this. So it will go here. So that where horizontal will go, which detector will detect anti-diagonal, vertical. So this is how you do the field experiment. Then you make your setup on the breadboard. You can make it more compact. That's what we have. We started a company, QTest Lab. We have started a company along with my student. So we can make it more compact, making smaller mounts, smaller optics. Okay, you can box it, you can take it anywhere. But when we are doing this lab thing, we like take the liberty of this optical breadboard, which is slightly bigger, and we make a setup. We take to the like terrace and do the field experiment. So this is the field experiment we are doing. Here you can see that this is transmitter Alice and this is reflector and it's being reflected received by Bob. So this is a kind of non-direct line of sight meaning. It's not indirect line of sight. Signal is being reflected and received by the Bob. Why you may ask why you have done that, why not directly? Because we took a project from DST and we were supposed to show like field demonstration for 200 meters and there are only two buildings which are 100 meters apart. So that's the reason. So and luckily it was 100 meters apart, fortunately, so we could get 200 meters and we could show that. So that is the reason for this reflection, but it's really a very good arrangement. And we could do that experiment. And when you do experiments, we started in sometime December, January, this experiment, first time. And things were very fine, we were getting very good data, but then this summer started and wind started blowing. And all this you see, this is on a tower and this reflector is there. So it started vibrating. So we are not getting any data. Then we have to fix this whole tower. Okay, get it fixed so that it doesn't vibrate when wind is blowing. So when you do experiments really, and then another thing you will notice here, um, here we tested everything in the lab. It was working fine. Data was coming good, but in launching optics, somehow we are using when we are setting field experiment, we are using dielectric mirror instead of metallic mirror. So dielectric mirror, if you're using, it rotates the polarization, changes the polarization. And we were not getting the right data. So it took at least 1 month to identify where is the problem, why we are not getting. So 1 month we wasted just to find out that by mistake, some of the mirrors are dielectric mirrors and we have to replace with metallic mirrors. So when you do experiment, these kind of problems you face, that's what I wanted to highlight. It's not very straightforward. And even in tangle photon source, I will come to that and what kind of problems you face, you will realize. So that's what it is. You make the setup and do, and then collect the data. So suppose Alice is sending H polarization state, and in Bob detector, which is supposed to get like H polarized state, it gets very high. So, and this kind of signal you will get only when you are selecting the right delay. Okay, 639 nanosecond because you are doing with 200 meters. If you this delay is even up by 1 nanosecond, you will not get this kind of signal. Um, so you can do that other measurement V very less. You see that, and what is the good point? How you test that everything is fine? You measure in D and A. So H, you are theory guys, you can write H as D plus A. So almost equal number of D and A if you measure. So you can see that your setup is fine. So if you see that D here all 200 plus, A here 200 plus, and then if you notice that it was 400 plus. So almost equal number of D and A, and that sums up to H. So your setup is fine, and since your setup is fine, you can extract the key, and you have to measure this channel parameters. You have to mean photon number per pulse. You have to verify channel transmittivity. You have to calculate, or you have to not calculate, rather you have to observe. Then overall detection efficiency you have to verify. Then depending on repetition rate of your laser, you can have like keys. Okay, you can increase it to 10 megahertz, gigahertz. You will have higher number of keys. And then these are the three instances of the experiment, and you can calculate like error bits, quantum bit error rate, and all those things you can do. Then, as discussed already, you have to do this error correction and privacy amplification. It has already been discussed. And then you get smaller number of secure keys. So this is the key rate. And what happens, this is like a 2017 paper, and this is generally when you are doing single photon detection, you are doing just single photons. You keep this term only one, okay? But if you are having like two photon detection, suppose you want to do, so you will have Q2 and all those terms, okay? And this is the mutual information between Ellis and Eve, and that you can calculate. This is important, and so depending on these channel parameters, you can. Why I'm showing that? Because it's connected with our new protocol, coincidence detection protocol, and interrupt pulse coincidence detection protocol. What we say that in coincidence detection, generally two photon pulses are discarded when you are doing BB84 and decay state. But we say we can use even two photons by measuring the coincidences. Okay, we can use two photon pulses also to make the key. Okay, so that's what we are doing, and we characterize the channel, and we know we can estimate what kind of coincidences you will get if you are having two photon pulses, and if it is like different, we can say there is some Eve attack and all those things, and what is the meaning of interrupt pulse? We send extra pulses like decay state protocol. We send along with CD, we do the interrupt pulse, extra pulses to monitor the channel. So both of the things we do, and we for finding the key rate bounds, we use the semi-definite programming. One of our colleagues, like one of our friends, Ritviz, he has helped us. He was doing PhD with Kolbak in New York, and he is Gujarati, Ritviz Bhavsar. So his house is very near to PRL. So when he visits his hometown, he comes to PRL just to see what we are doing, because he was knowing through papers. And then he told that he can do that semi-different programming, and you will see that if you do the analytical thing, decay state protocol here, for example, he has shown this decay thing, original paper, this estimation is this key rate, okay, for mean photon number. And if you do the semi-definite programming, you can get higher key rate. Okay, this is numerical technique basically. So that's what we do, and this is when you have single photon, you have two photon, you combine, so you get higher key rate. So we have done that, and we see that using this coincidence detection and interrupt pulse coincidence protocol, which is secure enough, you can have higher key rate compared to BB84 and decast protocol. So this is the basically that's what I was telling. You have to have this single photon yield here, single photon, two photon, and this semi-different programming. It optimizes this thing. Okay, this R thing it optimizes to give the bound, key bound. And then we were talking of this mitigation, this information leakage to the Eve, that side channel information we have to calculate. So this is source characterization for mean photon number purpose. So in BB84 or many protocols, we use many detectors, single photon detectors instead of one. Generally, what you do for mean photon number purpose, you have single photon detectors. You know the repetition rate of laser, how many pulses are coming per second. You have the detector efficiency, so how many photons you measure per second, you divide by that. you get the mean photon number per pulse. So just one detector is good enough. That's what you do. But here, since we use these 4 detectors already, setup is there. So we use these 4 detectors to do the rigorous characterization of mean photon number per pulse, and it gives the better estimate of mean photon number per pulse when we use these 4 detectors. Same setup as BBT4. Okay. So you will see if you have like second method, this 4 detectors being used for this mean characterizing mean photon number instead of this 1 detectors. This as you increase the mean photon number per pulse, it will lead to the difference. Okay, this is leading to the difference. 2 methods. Okay, as you increase the mean photon number per pulse, that's what we use. A higher number of mean photon number per pulse we can use when you are using coincidence detection protocol or EPCD. And this difference will lead to the higher information leakage. You can see that. Okay, this will lead to higher information leakage. Same way, this is like source characterization, mean photon number per pulse. Then there may be like we are using 4 lasers. Okay, so these lasers may be different in wavelength. That lasers may be different in pulse width. Lasers may be different in arrival times when pulse is reaching there, and then their pollution state may not be ideal, whatever you are making. All those things will lead to the information leakage. Information leakage in the sense you can discriminate if there are 2 different wavelengths. So based on the wavelengths, you can discriminate this pollution state. So that's the kind of information leakage to the EU, and that we have developed a technique like it's experimental friendly. Generally, this information leakage based on mutual information you do. Okay, it's based on probability measurements and all those things. Mutual information this between Alice and Eve. But instead of that, what we do cross correlation between 2 signals. Okay, and that's very simple. If you see here, just these traces you see wavelength. You have 2 traces for 2 detector, 2 lasers, and you do the cross correlation MATLAB. Very simple cross correlation function is there. You can do that if you have given signal. So you can do that, and with that you can calculate like mutual information. 1 minus cross correlation. So if cross correlation is 1, they're exactly same. So mutual information will be 0 to U. You see that IAE, that will be 0 if they are exactly same in all respects. So mutual information will be 0, there won't be any information leakage. If they are different, so that will lead to the information leakage to EU. So that's what we do, very experiment friendly. Depending on which variable, we change this setup here. We can use CRO, we can use photo detectors, whatever. So depending on what variable we want to check where they are different, we'll change the setup here. So we have calculated for pulse width, the wavelength difference, arrival time. What is the, and this you notice this is 10 power minus 3 bits per pulse. Suppose you are using gigabits, okay, your repetition rate is gigahertz. So 10 power 9 10 power minus 3, that will lead to megabit, 10 power 6. So bit per pulse, you are losing information. There may be information leakage of that order because of wavelength difference. Same way you can information leakage due to pulse width also. So see, if you are using like 10 power 6 or 10 power 9 repetition rate. Same way this correlation also, and even spatial mode. If spatial modes are different, that may also lead to the leakage. All will not be having same spatial mode. If you look into the CCD, they will be different. Okay, all may not be pure Gaussian. Okay, slightly away from Gaussian. So that may also lead to then population error you can calculate. For that also there might be. So you have to characterize your source. Okay. If you are making it commercial, you have to tell that this kind of information leakage for kind of equipment we are using. So you have to take into account. And then you can have like source side, detection side also you can have information leakage because of miscoupling to the detector. Okay. If we are doing miscoupling to the detector, there may be information leakage due to that also. That again you calculate mutual information between Bob and here Bob, because detection side you are doing Bob and Eve, that you can calculate. And we can see that because of coupling mismatch, you have this kind of thing in detector, and this is low coupling mismatch you will see that this cross correlation is different for both the cases when you have miscoupling and very low coupling mismatch, and then that will lead to the information leakage. So coupling mismatch at detection side also can lead to the information leakage. So all those things you have to take into account when you are doing practical quantum key distribution. So this is now we are shifting to what you do when you are having entangled photon source and how you use for quantum key distribution. This is one of the setups for entangled photon source. This is not the only setup which can be used for producing entangled photon source. There are many setups which can be used. You have to use setup which can give you two correlated photons. Okay. So this is for correlation entangle, but you can have like this is Sagnac interferometer. This setup is called Sagnac interferometer based. These two mirrors and this beam splitter. But you can have this linear thing. You can use beam displacers, two beam displacers. You can have laser crystals. So there are many configurations. You can use the Michelson interferometer. You can use Sagnac interferometer. You can have without interferometer. You can have this entangled photon source. So depending on your ingenuity, you can have different setup. You have to see that these two photons which are coming, they are correlated in certain variable which you want to use. Okay. Here we are producing correlation entangle, so we have to check that their correlation are correlated. So what it does, you have pump 405 nanometer laser, okay, and this is the non-linear crystal PPKTP. It's not essential that you will be using PPKTP always. You can use PPLN, you can use BBO, you can use BIBO. So there are many crystals depending on wavelength, depending on what is available with you, what is your budget, you will use. Okay. So these are slightly costlier. BBO is cheaper. BIBO is slightly costlier than BBO, and then because here these periodically pooled crystals, you have to maintain certain temperature, very precise temperature. Otherwise, phase matching condition will not be met. I have not put that slide anyway. Not a problem. So phase matching condition will not be met. Okay, I don't know how I missed that slide. No problem. So so this pump is going there, and this is non-linear, non-collinear. Why non-collinear? These two photons which are being generated from the pump, you see this red thing 810 by 405. This is non-collinear and degenerate. Okay, you can have collinear and non-degenerate. You can have collinear, degenerate. You can have non-collinear, non-degenerate, all sorts of things. What is non-degenerate? Non-degenerate means when you have these down-current photons are different wavelength. That is non-degenerate. Non-collinear, they are having different directions. Collinear, they are having same direction as pump. Okay. So these are the different phase matching conditions depending on the crystal and depending on when you are using PPKTP, depending on the temperature, you can have all sorts of things. Okay. So this becomes this PPKTP or PPLN, they are based on this temperature tuning. This phase matching, you have to tune the temperature. And if you are using BBO or BIBO, BBO or BBO, you have to tune the angle. Okay. Here you have to tune the temperature. So you need oven and temperature controller, and that adds the cost. And along with cost, what happens? This electronics, this temperature controller goes bad quite often. So that adds extra cost and problem. But this is the most popular crystal being used for entangled photon source generation along with PPLN if you are using like communication wavelength. So that's what, so this D thing here, you may ask, nobody's asking what is D. This is dual half-wave plate. So it works for 405 nanometer as well as 810 nanometer. Same way this is D PBS, dual PBS, that works, this PBS works for both the wavelengths, that's why dual. So you will notice why we are being, this dual is being used, okay. So we have to split the 405 as well as the 810 here, so that's why dual is being used. And this non-collinear photons, correlation So we have to see the correlation. So we are using polarizer analyzer. So once you fix this polarizer angle like horizontal, and then you rotate the angle of this, and then you say this kind of, suppose horizontal, and you are rotating the other one, you trace. Mm, mm, that you have to do calculation, and you can design like they are available. You have to do a mixture of two materials basically. Okay, which will work for one wavelength. You can combine two materials, okay, two crystals, birefringent crystals, which will work for one wavelength, that will work for other wavelength. It will be unaffected. You combine that, then you can. So that's what. So you get this kind of curve. Suppose you fix this polarization as d, then you rotate it, and these are the coincidence counts. Okay. So coincidence counts are very important. They are integral to the quantum measurement. That was the idea to use coincidence detection protocol for this improving the key rate. So that's what. So this is the visibility curve we call, and this visibility curve, using this coincidence counts or visibility curve, you can calculate the Bell parameter, and along with that you can do the quantum state tomography. You can make many measurements on these entangled photons, and with that number of measurements you can reconstruct the state. It's a tomography basically, reconstructing the state. So it comes out to very close to the ideal state. We wanted to have 1 by root 2 Hs plus Vv. So that's what we get, 0.975. And it's very stable source. You can see the single photon counts. Pardon? Here? Yeah, this one. No, this is the this is the arrangement. This is the box where it will go. Yeah, just cover. So it is very small cover, very small footprint. Yeah, this. Yeah. No, no. This is the, this whole thing will go into the box, so it's very, that's all. So it has been shown outside. Yeah, very small. So, and this is very robust. We wanted to send it as a payload, but somehow it didn't materialize. Okay, not a problem. So here HM word is coming. So, and I talked of single photon source, and Pranav was talking of like purity and quality and all those things he was talking about. So purity, you do the G to 0. So if it is very close to 0, it's quite good. And then quality, how you do? You have to do this HM thing, okay, to say that all photons are indistinguishable. In HM experiment, if you know that if the two photons are completely similar, then you will have dip. Okay, otherwise you will not get dip. They will be bunched. They will come together to the port, and there won't be any coincidence. When you get coincidence, when you have detection at two ports, but in HM, what happens? There are two photons, and they will either go to this port or this port, so there won't be any coincidence. So you will get dip, zero coincidence. So that's how you say that they are similar completely. So this coincidence detection you do, these are the uh, photons coming at the same time. So you do for different angles of polarizer analyzer. You measure that, and then from that you use the correlation coefficient, and you have been hearing all the talks. So using this, he talked about this Manik Banik. He talked minus you can put anywhere, and you can do the all four sets and do that. Okay, so then you could put this correlation coefficient, and you can calculate the Bell parameter. And if it is more than 2, you say they are entangled. So that's what you do, and then we have developed very robust entangled photon source because we work with like structured light, perfect optical vertex beams. So here that idea has been used to like fix the, like to make it more stable, this SPDC ring. Because as the temperature changes, this crystal, this SPD searing site changes. Or if wavelength mode hopping is there, wavelength is changed, their SPD searing site changes. And generally, when you are making entangled photon source, you couple through the fiber, you take it out too. So fiber positions are fixed, so there won't be any coupling if ring changes. So to make it like uh, stable, this to avoid this change because of this temperature and wavelength, we made it perfect ring, and for that we use hexagon and lens. Okay, so using this arrangement, we can make it a perfect ring, and then we will not have any change as we change the wavelength or as we change the temperature, and that way we can have very robust entangled photon source. Uh, and then once we have this entangled photon source, we can have BBM92 protocol or ECART91 protocol. ECART91 protocol, generally it is not done because it gives very less number of key rate, and more resource you require, more number of detectors you require. So generally you do BBM92 quantum key reception protocol. And it's similar to BB84. Again, you random basis you select for polarization, you do the measurement. Okay, you assign bits to the, already I think Pranav has explained BB84. You assign these bits to the polarization states. Okay, and then you do the shifting and then error checking, whether even in same basis you have selected, but instead of horizontal, suppose you are getting vertical, then this will be the error. You see here, this is like diagonal basis, and okay, this is the state. You have assigned 0, but you are getting here, you see, last thing, you are getting anti-diagonal. It's same basis, but anti-diagonal, so this is leading to error. So that's what you talk of the error. So here, as I told, this is entangled photon source, and 2 photons you send, and then rest is similar as you do the VP84. So this entangled photon source is sitting there, and other arrangement is same, but here you see, you require more resources here. There you only 4 detectors you are using, here you require more detectors. But what is the advantage here? You talk of like random selection of the polarization state. Okay, if you see here, this random selection is being done by beam splitter. You are using single photons here. They are the 2 photon pairs. Okay, 2 photons are coming. So 1 photon is going this side, 1 photon is going to that side. Okay, wow. And because single photon, this beam splitter will do the random selection. So you don't require here random number generator to do the basis selection. So that's the thing, very important. You don't require here random number generators. And then you do the measurement, and time stamp is again important. And so this is the arrangement. You will not believe if you see this pan paper in 2025 PRL. Using single photon source, using quantum dot. They have done quantum dot single photon source. And somehow I was surprised, he has used the similar setup. Okay, this reflector thing, you see this PL paper, pan, quantum dot single photon source. I was surprised just 200 meters he has taken, and this reflection thing. I was surprised whether this is my set, my scheme, or pan scheme. And they have published in PRL this quantum dot single photon source. So that's what they have done. We published long back this paper. So you have this Alice Bob 200 meters. We can do 35 meters. And this is the entangled photon source here. One is going to Alice and Bob. This is just schematic, Charlie Lee entangled photon source. Okay. So then after this distribution, you measure the entanglement. Okay, so you measure the Bell parameter. It's coming 2.54 plus minus 0.06. Quite good. And your confidence window is 1 nanosecond. And that I explained already. You fix H, then rotate the polarizer, other polarizer. You fix V, rotate the then. So you can have this kind of curves. Okay. And these upper and lower lines are like 98% confidence intervals, and middle is theoretical fit. So based on this visibility and confidence count, you can calculate the Bell parameter as explained. Then here also this timing is very important. You see that instead of 689 seconds, now it is 648 nanosecond. You will notice that now setup has been moved into the same cabin. I have not put that, but setup has been put into the same cabin, and distance has reduced slightly. So that's why this another number here coming, this delay thing. So we are having HS plus PV, so we have to take diagonal thing because HS plus PV, you can write DD and A plus if you go to diagonal basis. So these diagonal numbers will give you the key. If you sum up, you will get the key. So that's what you are getting. And then you have to do the error correction and price simplification also. So you can study the effect of atmosphere. That's what we have studied. Certainly atmosphere, depending on atmosphere, key rate will be changing. So that's what we have verified for 35 and 200 meters. And when you have high number of high concentration of aerosols and low concentration of aerosols. So this is mm. Some people get confused. This is mm. This is typo or what it? It's not typo. This is megameter inverse. That's how you write when you are doing atmosphere thing. Okay, megameter inverse per megameter. And scattering is also per megameter. This is microgram per meter cube. Okay. And then another, we are trying to do that device independent quantum key distribution. Okay, that's what it is. So we use HM setup, Hango Mandal interferometer setup. Here these two photons coming, and then they are being combined, and you do this HM experiment. Okay, you record the coincidences as explained here, HM setup. So you record the coincidences, and by changing the like you then when they are perfectly indistinguishable, you get like this kind of dip. You can reduce the indistinguishability and you get a high Bell parameter. If you from this you project a certain polarization and like you can create all sorts of Bell states using HM by changing by using the proper polarization optics. You can get all sorts of all four Bell states using HM. And if you are going away from indistinguishability, you change the Bell parameter. So you can spoil the Bell parameter, and this is the relation between this bit error rate and Bell parameter. So what we say, since they are related, Bell parameter and Kuber, okay, and this comes from where? This is like you calculate mutual information between Ellis and Eve in terms of Bell parameter, their expression, and from that you can translate to how it is related with Kuber. Okay, so that's what. So you can relate your Bell parameter with Kuber. So just by looking at the Kuber, you are doing the quantum key distribution. You can say that this is the Bell parameter. Okay. So you can do that for all Bell states. That's what we are showing. And you can have mutual information. You can calculate mutual information between Alice and Bob as well as Alice and Eve. So, and if this thing is positive, like if you are below this 4%, this is positive, okay. This AB is, IAB is more than the IAE, okay, mutual between Alice and Eve, you can have positive key rate. So if you are below this 4%, you can have like Bell parameter, you have more than 2, and you can have positive key rate, you don't have to verify. So it's kind of device independent. You are doing Bell parameter, always you have like more than 2. If you are below that, you are verifying Kuber, and so you can have device quantum key distribution. And this is like um, how to integrate your fiber thing to free space. That's what we have done along with CDOT. And this is like a CDOT system, fiber. We are having a free space system. We are having K2 here, and they are having K1. And then again, like satellite, we take this as trusted node. We do the K1, K2 jar, and another jar operation will give you the same key at both ends. And then you can do, okay. So this is trusted node here, fiber and free space. Trusted node, you can have integration of fiber and free space key distribution. And this is very important for if you are developing network, okay. Not going to that. So this is future plan, and thank you. You can have questions. Um, for same thing, you can have many methods. I like heralded single photon source I told. So that was free space. You can have fiber. You have 1 by 2 fiber, 2 by 2 fibers, okay? So you can use all fiber thing for heralded single photons. You don't have to use beam splitters. What you do, if you want to make alignment free thing, this is coming here. You do this 2 by 2 thing, okay? 2 by 2 fiber. So this fiber you couple, and then you another same thing 1 by 2 fiber you couple with, and then you do the coincidence count. You have this. So you can have depending on your like choice. You can have fiber. You can have free space optics for same device. You can make it compact. You should know what are the things available with you. Okay, so you can use accordingly. Mm-hmm. Where? What? Entangled photon source. Hmm. Hmm. I I didn't notice. We can one maybe for laser and uh, hmm. Maybe there might be three-way and you are using just two. That must be available in the lab. They must have put. I don't know exactly. I will have to see carefully. I didn't notice. But sometimes it happens. You don't use the other port. You have three-way. You just put and take the photograph and all. Like 2 by 2 coupler, you take fiber. You just use one. So the same way you can have it. It's okay. So 2 by 2 coupler you don't use one. Just use one. So it may be there. Yeah, not a problem. Hmm. Single laser you can do polation modulation, okay, if you are using BB84, okay. But they are not very good, these polation modulators. Speed is also not high and this modulation is not very good. Like if you want to make HV, they don't give very good polation states. That's the problem with polation modulators. Okay, it's not a net good quality. Good part of PL is that we have space and atmospheric sciences division. We have many divisions. So there are researchers who take hourly data. There are instruments which collect hourly data, like surroundings, where we are doing experiments. They have hourly record, 24 hours. You can take data from that. So all the aerosol data or extinction coefficient, all their hourly data they collect, and from there we have taken these atmospheric parameters. Yeah.
Can you hear us?
Pardon? Entanglement sudden death. So here I have not talked of entanglement sudden death. In this kind of setup, sudden death, how you will have, there are cases when we are studying this position momentum entanglement, there we observed sudden death, okay, when this beam is elliptical. But here I have not observed sudden entanglement death in this setup. So I have not thought of this question whether we can have this sudden entanglement death in this kind of setup. I will have to think. I don't know exactly in this setup. But you will see our paper in physics letter A, position momentum entanglement. Okay, we have done that. There we talk of this sudden entanglement death.
Sir, my question is like we use entropy accumulation theory for calculating the bound on the conditional minimum entropy, then why do we want to go for SDP? What is the like motivation for?
SDP as it's told that this gives you better bounds. Okay, it's hierarchy rate, and this is like a very good numerical technique you can use, and it gives. It's being used many places, not only many optimization problem. This semi-different programming is being used, and here it gives advantage even for decay-state protocol that it gives high key rate. So that's the motive that you get better bound for key rate.
And sir, one more question. In one of the slide, you have shown Cuber for 35 meter and 200 meter.
Yeah.
So I think the for the 35 meter, if the Cuber was high as compared to
Because
200.
that's what the atmospheric effect. If like extinction coefficient is very high that the atmosphere is dirty, so Cuber will be high. So that's what it was showing the importance of the aerosol concentration in the tube.
Thank you, sir.
So you mentioned that you are also able to do device independent
Yeah, that's
QKD.
what I was saying. You have like Bell parameter mode, just looking at Cuber, but you monitor when you're doing QKD. So you don't have to do the Bell measurement, extra Bell measurement. So just by Cuber, you can infer that this Bell parameter is then 2, they are entangled. So you can have this. This is a kind of device independent. You don't have to devote extra bits, like extra, you have spend the chance Bell inequality violation.
Oh,
Yeah.
so yours is like full device independent or measurement device independent or
Because it based on this entanglement, we device independent, yeah,
device independent?
instead of measurement device independent. Yeah.
I see. So, so can you say a bit about like all these protocol, all these protocols which are, they say that implementing fully device independent QKD is not easy. You don't get good rates or whatever, and therefore people go for measurement device independent and all that.
So
So
I don't see there is a problem if you are below. If somehow you can keep your Cuber below 4%, I don't see any problem. You can have positive key rate. That's what I feel. Key rate maybe not very high, but you can have positive key rate if you are below 4% device. Yeah, he is
I see. So
right.
you
That's
assume
what.
independence.
Yeah, now he is pointing. This relation for mutual information between Alice and Eve in terms of Bell parameter, that is for individual attacks. That relation, from that it has been derived this relation between Cuber and Bell parameter based on that mutual information expression. So, but we are working for more rigorous expression, taking into account collective and other attacks, to get better expression for Bell parameter in terms of this Cuber. Once we have that, then we can say this completely, it is safe against all the attacks. So that's why we have not published in the journal. Still, we are working on that. This is archive paper. So once we have that expression, this much more rigorous expression, taking into account collective and other attacks, collective attacks, then we can have this
I see. So for now, you're assuming these
individual,
independent attacks or something.
individual attacks.
And are there other groups in India who have attempted device independent QKD, for example?
Not too much. MDI QKD is implemented, fiber. I told that I will mentioning other groups. So this fellow himself is doing this fiber-based QKD. He has set up from CDOT, and they use for their experiment. They verify the setup. And CDOT is quite advanced in Delhi. They have done like COW, current one way, as well as DPS, differential phase shift keying, in fiber. And there is group in IIT Madras, Anil Prabhakar. They are mainly focused on fiber. They are again on DPS. They have done. They are developing a network, fiber network. Okay. They have done like 3-node network. They have done in IIT Madras, and then they want to go for longer fiber-based network. Then there is group in IIT Delhi. Bhaskar Kanseri and Joy Ghosh, they are also working on this fiber-based quantum key distribution. Bhaskar says that he has done fiber-based quantum key distribution using entangled photons. as well as weak coherent pulses. And Joey is also going for this free space thing using entangled photons. Joey Ghosh in IIT Delhi. Then here itself in Bangalore, RI, they also do this quantum key distribution. Okay, free space, not fiber. So there are many groups in India who are doing like fiber-based quantum key distribution as well as free space. So um, we are not the only one. This Anil also doing. Anil is there, Bhaskar is there, Joe is there, and then there are other colleagues who just chip in some part, like Seth Natarajan, he helps in FPGA development for processing the data. So there are other groups involved with that, but CDAT is there. And now companies are there. CDAT has transferred technology after developing the COW and Coherent one-way and DPS. They have transferred the technology to New Age, and New Age is commercializing the setup. Okay, so they have got certain orders from defense, and they are supplying. So companies are there which are giving this setup, selling that setup. So things are moving in India. It's not like a very bad situation here. And we have company, QTES Lab. You can remember that. So we are also going to have entangled proton based quantum key distribution setup. Already we have entangled proton source, okay, Herald single proton source in our, like we have set up, we can send to anybody. And we have QKD demonstrator. It's not QKD analogy, quantum cryptography analogy demonstrator. I don't know. Somebody was making syllabus for undergraduate minor course, and they were making what should be the lab experiments. And I don't know how they saw the whole lab title, quantum cryptography analogy demonstrator, and it has nothing to do with quantum cryptography. I don't know who was making the syllabus, just picked up from there quantum cryptography analogy demonstrator. It's all classical, nothing quantum there, and that was put. Here we are struggling to make QKD demonstrator real, okay, how it is done. But this UG minor says quantum cryptography analogy, and they can sell it 3 to 4 lakh. And when you do, do this real QKD demonstrator, it costs you 20, 25 lakh. So I don't know now. We have that how to sell it. But you can't sell something wrong here. This is misleading thing. There is nothing quantum there. I don't know who has made the syllabus and put this experiment there. So I am being asked now with my investor is asking, you go and give talks. Why don't you tell the fellow who has made the syllabus? You change that. Who has made that? You ask him to correct it. So I told, okay, I will try my best to convince the fellow to correct it. I don't know who has made the syllabus. He is smiling. So that's what it is, yeah.
Are there some groups which are also attempting satellite QKD?
Satellite QKD, we are supposed to do that. Basically, in 2015, history is very old. We put up the proposal, full proposal with budget, manpower, everything, to Principal Scientific Advisor, Government of India. It started from there. So it was forwarded to ISRO. You follow it up. ISRO, I was called to ISRO. I explained everything, and then they started taking interest. ISRO chairman visited PRL, you submit the proposal. We submitted proposal from PRL side. So it was told, no, you get involved with other ISRO units and all those things. PRL cannot do alone. Other units got involved. Gradually what happened, it was hijacked from us, and we are nowhere. So ISRO unit has taken now satellite-based QKD project, and PRL is nowhere. So that's how happens in government organization. So that's the story. So
But
ISRO is trying to
Israel
do
is doing.
expected to do, I don't know, but they don't have any scientists involved there. They have engineers, team of engineers. I think they are young engineers and a good number of engineers. Okay, and they can do that. It's not like that they cannot do that, but it will take time. They promised to do it in 2 years, but still, I have been asking since 2015, many DRDO meetings I attend. I am asking to make ground station. You can send the payload. Making payload is not difficult. In 6 months, you can make the payload and send it. But how you are going to receive the signal if there are no ground stations, visible ground? But till date, there is no optical ground didn't receive the signal in India. So that is the status. Now they are trying to buy complete ground station from Europe somewhere. Okay, instead of developing that, and they're saying they will do it in 2 years. But problem is that even in Europe there is no working ground station. No company has made working ground station because there is no satellite-based quantum key distribution except China. There is no. So working ground station is not there, although they are saying that they will do, but you don't know. Like even if you add a telescope, a telescope, it takes lead time is more than 1 year. So making in 2 years ground station is not possible. So it will take time. They are working on this, but it will take time. It will come. And that is like one of the objectives of NASA quantum mission. So we are supposed to do that as a country. So we will do that, but that's it.